Okay, I'd like to start today's lecture with analysis of thinking about a rigid body, how that thing actually works. Yeah, because now let's say, I mean, I made here a rigid body from those markers, and now do we see? Oops. Assuming that it didn't break, do we see that it's a rigid body? Can we see that this is a rigid body, right? Because, I mean, it is that the relative configuration stays the same all the time. Well, now let's think about using this for, let's say, as a post, for example, or a pole to support something. I can squeeze it, right? And that way I can transmit force which I apply to this one to my by my left hand to the right hand, or I can push that way, Jessica, right? Now, how about if I try to pull you? It didn't work right. Yeah, I mean, it doesn't look that this is a good body. I mean, how about if I try to pull Jessica with a ruler? Can I do that? Who believes I can pull her with a ruler? That's good. Yes. Why I could pull her with a ruler and couldn't put her with the markers? Now, I mean, those markers when they were made as a single rigid body. Well, what do you think? Why that thing didn't work and this thing did work?
The particles in the ruler are strongly attracted to each other.
Aha! Particles in the ruler are attracted stronger than particles in this body. I mean, particularly in those places like between this green block, green marker and blue marker, right? Over here, the particles don't hold each other pretty strongly, so it's easy to separate them. Well, it is important now what type of how strong is the internal interaction within this system. So how about now I make an experiment. I brought here several of those. Could you hold this for me? And how far I can bend it, and now if I bend it, I mean, where is it going to break? Yeah, because now we also have, I can look at this rod as markers connected to each other, right? Half of the rod is also a rigid body, right? Now, how come that this is, well, before I even break it, let me mark, let's say that over here I mark it. So this entire rigid body is actually composed of one rigid body here and one rigid body here. And now if I look at this part, how come that it actually stays in this place? Well, this rigid body stays in this place, right? It means that forces exerted on it balance each other. All right, let's identify the forces exerted on it. How about if you even draw it on the board? So here I have this rod. Half of the rod is an object which I'm considering, and it's a rigid object. And let's draw a free body diagram, marking the forces at their centers. So, what forces can you help me to identify here? Just for this part. What? Gravitational force. We have gravitational force. And center of gravity happens to, for a uniform object, happens to overlap with center of mass, and it is in the midpoint of that rod. Right now, this is one end of the rod. This is the other end of the rod, the one which I'm considering. So center of gravity is over here. I have gravitational force. All right. I made it too long because I won't be able to draw the other one. All right. What else?
Equal and opposing forces all.
Yeah, there must be an opposing force, a force which balances this force. So who can exert a force upwards now? Yes? The other end of the rod. All right, now let's try to figure out where is the center of that force. Correct. This part of the rod now pushes this one up. Now, this part of the rod interacts with what part of this? What particles of this one?
Very first one, right?
Only those at that surface over here. So the center of force will be somewhere over here. I will call this force S. I will use symbol S for that. Does it now takes care of that? Does it balance now the rod? Can we see that according to this free body diagram, that part of the rod should remain stationary? Can we see that? Who can see it? Who cannot see it? Those of you who cannot see it, you are right. I cannot see it. Because now, I agree. I mean, you probably came to the conclusion, well, the net force exerted on this object is 0. Well, if the net force on the object is 0, how the object moves? I mean, let's say that it starts from rest. If the net force is 0, how the object is going to move? How? Shout. I have the answer, stay still. I disagree. This is not what Newton's second law says. Yeah, remember, because I mean, it would stay still if you think about this part as the particle. But it's not a particle anymore. Start thinking in terms of objects. So, you were kind of right that it will still stay still. In what sense it is going to stay still? Yeah, let's recall appropriate version of Newton's second law for an object. If we want, we can talk about acceleration. So what acceleration of the object is proportional to the net force exerted on the object in an inertial reference frame? Acceleration of the center of mass. So the only thing which you can say right now is that the acceleration of the center of mass is going to be 0, right? Now, how about if we consider torque? Let's consider torque about this point, the center of mass. What will be gravitational torque? 0, because the center of the force overlaps with the center, with the point about which we consider torque. How about the force, the torque exerted by this force? I mean, resulting from this force? Torque is toward us, right? So it tends to spin. It would have to start spinning that way. If this was the right free body diagram, it would have to start spinning. So there are some, well, more than that. There is a torque missing. Now we have to do it, we have to supplement this free body diagram in such a way that the net force, we will not affect the net force, so the net force has to be still 0, but we have to change the torque. So whatever interaction we include now should result only in a non-zero torque, which two forces, you mean, which means that we have to apply at least 2 forces. Because if we apply 2 forces which are opposite to each other, then it would not affect the net force. However, it is going to affect the net torque. All right, so we need now, I mean, since we figured out the torque of the forces which we have right now is toward us, we need it in. Consult with each other, where could we find interaction which would result in with torque in? Of what? Over here? Over here? All right. Yeah, with my hand, well, with my hand, I'm interacting with that part of the rod. I'm not interacting with the other part of the rod at all. I'm not applying that torque. I do not interact with this part of the rod at all. This part interacts. And precisely it interacts only over here. Only the particles of this rod on this over here at this end interact with particles of this part over here. I am not interacting at all. Which actually I gave you already a hint. Who exerts the torque? Which rod? This part of the rod now has to exert a torque. How can it do it? Well, if we need a torque that way, which means that this rod over here has to push bottom side to the right and top side pull top side to the left. Can you see that? Yes. Now torque. Yeah, I mean there is a very small lever arm over here because this is the line of the force, and the distance between the point about which we consider the torque and that line is small. However, the line of the force does not pass through the point about which we consider torque, which means that it results in a torque. This force results in a torque in, and this force also results in torque in. Now, let's see what will happen if I start to bend it. And let's say that I bend it this way. I'm trying to bend it in such a way so that this thing breaks somewhere in the middle. Yeah, and I achieved that. However, if I want, actually, I can now do it in such a way that it breaks next to my right hand or left hand. Yeah, I want you now to practice this a little bit and try to figure out what actually you are doing when you are breaking it at a particular point. Yeah, so have this and play with it and break it at various points and see how to do it so that you do it, that you break it in a particular way. Have it. Okay. Have you figured it out? Yeah. Would you do it? Okay. Oh, great. All right, give a piece. Would you like to practice it? Try to break it at various places. And actually, what you are doing is a very important thing in designing, particularly in civil engineering. It happens that I don't remember if I mentioned it already or not. My sister is a civil engineer, and all the beams in the buildings experience these types of internal interactions, and I hope that you will pick it up at the end, okay? Can I ask you that? She has to understand what happens when, well, experimentally, you actually probably already figured it out. So, for example, if I don't have any, if I wanted to break this ruler, I'm not going to, if I wanted to break this ruler at the right hand, what would I have to do? How would I have to interact with that ruler? No. I had to apply a torque over here. I have to twist it, right? Have you figured it out that actually in order to break it at one end, it was not that you pushed it stronger, you twisted it at the same time, right? That additional twisting, so you apply different torque at this point than at this point. All right. Now, let's see actually how to determine where is the weakest point of such an object, depending on the location. So for example, if it is standing just like this, where is the weakest, I mean, it isn't the weakest point really, but where the internal interactions has to be the strongest? Some of you will say over here. Why? Yeah, because now look at that. If I consider this part, this cross-section over here, this part has to hold that part, right? So if I consider, let's say, this cross-section, that part holds half of the rod. Now, if I have a cross-section over here, it is much heavier rod, right? Now, if I take it over here, it is much lighter rod. Do you understand that? Yeah. So, and actually, when you consider now the distribution of the internal interactions which holds the piece together, you can do it two ways. Either consider all forces which are on the left or all forces which are on the right. It doesn't really matter. So how come that this piece, for example, stays in place? I can do it the same thing. Yeah, over here I was applying two forces, one force up and one force down, and then when I consider this piece over here, that part, although it's in air, it balances the forces and torques for this piece, even although I was doing here. Doing that. Do you understand that? So when you will be in more advanced classes, you will actually analyze and draw plots of forces along this entire beam and torques along this entire beam. All right. Now I would like to go to analysis of internal interactions, and how actually internal interactions depend on the shape of the object, because really the shape of the objects makes it what forces exist inside the object. So now, first thing I would like to do is to review the types of materials we had. And depending on the properties of materials, we use them for different purposes. So let's start with objects made from solid substances. This rod, the ruler, these were solids. And in solids, atoms are arranged in a certain configuration, and they almost remain that configuration. There are some vibrations about equilibrium locations of individual atoms, but atoms do not travel around the entire substance or entire object made from that substance. However, we have also substances in which particles actually can travel. The interactions obviously, well, not necessarily. They don't even have to be necessarily weaker. Fluids are very strong for compression. However, I cannot pull Jessica using water or any type of a fluid. I will have to use solid, or even a rope. Although it is very flexible, it is still solid. If it happens, then in a solid, atoms are arranged in a particular lattice, a pattern, which is extended across a long range. We say that this type of solids are crystalline solids. So if you take, for example, a crystal of sugar or a diamond, if you have a ring, in a diamond, for example, the atoms actually are arranged in this configuration. This is very close configuration to a configuration in a diamond. You can think about it that it is a cube, and you have an atom in each corner. You have you have an atom at each center of a wall, here and here, and then you have another cube actually which is shifted 1/4 along 1/4 of the diagonal of the, so this atom is inside. Yeah, this one is on the surface. This one is inside. This one is inside, and this one and this one. These are inside the cube. All the others are on the surface. If I move through diamond, over there will be identical cube, and then next cube, and up a cube, and we will have to. This is a building block of a diamond. In amorphous substances, we don't have this long-range order. It is that in the vicinity of a particular atom, we have the other atoms are ordered, but we cannot extend this order throughout entire object. Fluids, well, there are three types of fluids. There are liquid, gases, and plasma. In liquids, molecules interact relatively strongly. Water is, for example, a liquid, and this is here I made drawing of water molecules. And water molecules, they travel throughout the volume of entire water and bounce off each other quite often. And well, this would be really like a tight crowd of people. And think about how you can move in a tight crowd of people. This is what happens in a liquid. A major difference between liquid, or in general fluid and solid, is that a solid, if we make an object from a solid substance, it will maintain its shape. Fluids won't. Fluids cannot maintain their shape, so they always assume shape of a container. I mean, maybe not always, because if I take a water and let it in spacecraft, let it loose in spacecraft, it will really become a bubble, a round bubble. Gases are substances which, and actually both gases and plasma are substances similar to water, except that the interactions are much weaker. In gases, molecules very rarely interact with each other. The only interaction with them is that from time to time they have a collision. Two molecules of air from time to time have a collision. Now, do you remember what is a collision? It was a brief interaction. Yes, so throughout the time of, I mean, if we compare with the time of having, let's say, gas in a particular container, and compare that time to the time when it interacts with other molecules of the gas, then interaction will happen in a very short period of time compared to the time scale. It is more probable that gas molecules do not interact at any particular instant. In case of water, it is that they do interact. Plasma is a rather rare state of matter in our environment. It requires very high temperature, and it requires so high temperature that actually atoms are ionized. Electrons are taken away from cores. All right. Now, obviously, if we think about describing interactions, internal interactions, and we look at individual atoms, we would become mad. Because even if I think just about cross-section over here, the number of atoms is too large. So we have to develop a better description of this interaction than interaction between individual molecules? Well, I want now to introduce today certain physical quantities which describe that interaction between well, it will not be between individual atoms, but groups of atoms. It is the similar trick, like instead of calculating moment of inertia, we didn't, or looking for the center of mass, we didn't add contribution of individual particles to moment of inertia or to the location of center of mass, but what did we do?
Sum them all together.
Yeah, we summed them together into an object which we still could consider as a particle. How did we do that?
Integrated them?
Right, yeah, but before, correct, we integrated rather than added. Yeah, so rather than added particle by particle, we divided object into differential fragments, and each differential fragment already had thousands of particles. However, if those particles were within this differential fragment, we could consider still the differential fragment like a particle with mass equal to the sum of masses of all particles which were in the differential fragment. Do you understand that? Do you recall that? Well, this is what we are going to do over here too. So rather than thinking about individual particles, we have to imagine a tiny cube within the substance. So imagine that inside, well, this block, this rod is, rather than thinking that it is made of individual particles, think that it is made of blocks of particles. Still tiny blocks of particles, differential blocks of particles. And, well, each of those blocks inside of that object, what does this block do over here in this rod? How does it move?
Stay still.
It stays still, right? Which means that the surrounding on that block interacts with it in particular weight. Yeah. The block has weight, for example, right? So there is a gravitational force exerted on it. How come that it doesn't fall? Because the rest of the block interacts with that. And actually, if I start to bend it, or to stretch it, or to compress it, that block actually reacts immediately, right? It does not accelerate. All right, so rather than forces, we introduce a concept which is called stress. Stress inside of an object. And we have to consider this differential block inside of the object, and stress is defined by the forces which are exerted on the walls. Because the surrounding now exerts forces on each of the walls. And I can mark the center of the force at the center of each wall. So for example, at this wall, I have certain force exerted by the surrounding. At this wall, I have certain force exerted on the surrounding, and on this one, I have certain force exerted on the surrounding. I take those forces and divide by the area, and this gives me the components of stress. So I know that this is a new concept for you, so you have to really to concentrate on that. Let's analyze actually what is what of what. So sigma ij is a component of stress. Now I and j can vary. These are subscripts which can vary. You can have x, y, and z. Yeah, these are the I and j refer to appropriate components. All right, number I, the first number, says which scalar component we have to take in evaluating stress, and number subscript J tells on which wall. So, for example, consult actually with each other why this. Over here I already marked the components. So force is really somehow at an angle. Why this component of the stress has subscripts x, x. Consult with each other. Why is it x, x? This arrow over here. Have you got it?
I think so.
Okay, I think JD has a comment how we can do that. Yes, so let's start first. Why do we have this first x?
Unless the particle is sitting, or the spot is sitting there actually the particle sensitive.
No. Let's take a look. I represents the scalar components of the force. Yes, it is in the x direction, therefore this subscript is x, right? Now, this is not just by a single particle. This force which we take over here results from interaction of all particles which interact with this surface inside of the body. But if we take x component of the force, then it will correspond to the first subscript x. Now, why the second subscript is x? Because this is the surface that facet of the cube is facing x direction, right? So look that all three have second subscript x, right? Because it refers to x wall. Now that wall is facing y direction, so we call that this is the y wall, and therefore second subscript over here is y. And this one is z, so second subscript is z. All right, so let's consider now that the same coordinate system, so x is toward us, y is that way, and z is this way. And I squeeze it. Yes, I'm applying a force in this direction, which means that the cubes are only squeezed from top and bottom. What would be the components, non-zero components of the stress from those 9 which you see on the screen? Which of them would be different than 0? Most of them is going to be 0 under such stress. If I squeeze it, I create a stress which will have really only one non-zero component of the stress. Which one? Consult with each other. Talk to each other. Mark, did you get it? Do you know that?
I think so.
You think so? Let's see your guess.
All the components that have the zx, the zz, or the zy.
They are non-zero. All right, so Mark thinks that all components on the z wall will not be 0. These, yeah. What's that?
Not there's no z wall. The zx on x wall, the zy on y wall, the zz on z wall.
Oh, I see. That this one, and this one, right? Somebody came with another answer? Did you come with another answer? How about you? What was your answer?
I didn't have an answer.
Okay, what was your suggestion? Just zx, z. No, Zx, this one, and this one. This one is 0, right? Okay, some other ideas? JD says that only ZZ.
Yeah, just Z because it's going to apply on that wall. All the other walls are not being interacted with that force.
So let's vote actually who supports who. Yeah. So who supports more? I mean he actually. I mean I like that all of you picked the vertical ones. This was smart. Really only vertical ones. Now Mark said that all 3 vertical ones. You had Andrew, right? Andrew said that only on the side walls. And JD said that only on the top one, only the top one. So who thinks that all 3 are non-zero? Who thinks that only on the side walls are non-zero? Andrew, you don't think it anymore? Or you changed your mind? Who convinced you, by the way? JD. Okay, so who supports JD? Well, let's now think about the neighboring cube then. Where's the black pen? All right. Here. And this one. The one in front, actually. Yeah, so I will not draw it for a moment. Yeah, so let's say that on this block we have a force up, right? Now that force up is exerted by the block in front. So I will mark that block in front. Not with this pen. And actually only the back wall, right? So how this, which means, I mean, this component of stress is related to the force which is exerted by that red block. How the blue block pushes the red block then? Down. Actually, now I think that it may be better to rotate this drawing and have it this way. So here we have a block, and we have a force exerted on it up, which means that on this block, we have a force over here exerted down. Now, what would be on this side? Up? Well, then it will start spinning. Well, looks like that. And then the next block will have again forces up. Is that right? Now, I can actually make those, divide those differential a little bit different, make them slightly smaller or slightly bigger. Don't you see that it wouldn't work? It wouldn't work that way. These, when I mean, something like this could happen indeed if I if I push this rod just at a point, just over here, right, with a tiny, I mean, very applied to a very small area. So now I can see that those blocks over here will hold it upward. Yes, so for example, indeed, if I stand on the floor here, so how come, I mean, I'm squeezing this part of the floor and pushing it inward. Well, how come that it doesn't go inward? Because this part holds it upward and this part holds it upward. So it creates this type of a stress. However, if I push it uniformly like I did, I applied force everywhere from the top. I did it that way. Right, so I squeeze from all through on entire surface. So indeed, the only component which is not zero is the ZZ component of stress. Now, the components of stress which are perpendicular to those walls are called compressive or tensile. So these are tensile compressive stresses, which squeeze the walls. Now, the one which are parallel to the walls are called shearing stresses. So ZZ refers to compressive or tensile stress, and it depends on this if we squeeze the object or if we stretch it. Now, probably you noticed that I didn't mark components of stress on the remaining 6 walls. And actually, on top of it, even those 9 are not completely independent. In order to have this block in place, those components of stress are related. So, for example, this shearing component must be equal to this one. If they are not equal, that block would start to spin. Well, in this direction, about x-axis. This component must be equal to that component. Otherwise, it will start to spin around y-axis. And the same thing is for these 2. So from those 9, we have only 6 which are independent. All right. The unit of stress is Pascal, and I think you heard unit Pascal already. Now, where? Pressure, correct. You heard that Pascal is unit of pressure, so it's possible that you heard it watching Weather Channel on TV, because they would say what is the pressure in the atmosphere. Pressure is also, pressure is one component of the stress. We will talk about this later. All right, and only 6 are independent. Now, in order to, I mean, how is it now that the substance creates stress and reacts to those forces? Yeah, why is it that, for example, I can walk on the wall, on the floor, and why can I squeeze those markers, and they react, they adjust itself, well, we recognize what force, for example, the pens exert on my hand now. So let's think about my left hand. What force is exerted by the pen? Support force or normal force, correct. It's normal force. Now, I told you that normal force is kind of smart force. Do we remember what did it mean? That it adjusts itself it reacts to me. The stronger I push, the stronger it reacts. Now, how come that it is so smart? What actually does the material do that it reacts this way? Well, I'm deforming it. It's exactly the same way like a piece of rubber band. If I stretch it, when you change the shape, then it starts to exert a force. Now, rubber band is does not react really fast. A pen or a wood, they change shape by a very tiny amount and exert huge forces. So when you walk on the floor, you think about it that every time you walk on it, you bend it. If you don't bend the floor would never exert support force on you. All right. Now, how an object is bent is described, this is called deformation. And we have a physical quantity. I want to introduce physical quantity, which describes deformation. We do it in such a way that if we initially have a block, and this block, when it changes the shape, when the entire object changes the shape, from that regular block we will get a parallelepiped, which means that each of those three corners will change position. Now, by how much that position changes is related to components of a physical quantity which is called strain. And I know that in common language we very often confuse word stress and strain. We confuse this because they are so closely related. In order to produce strain in the substance, you have to strain it. In other words, change cause a deformation of that object. Because we borrowed these terms from physics, and Scott Joplin, for example, wrote a piece, Strenuous Life, that he maybe means stressful life. Are you under stress now or under strain in this classroom? But obviously it refers to mental state rather than physical state, but actually this is where the phrases originate from. All right, so now ijth component of strain is defined by displacement of ith corner in the j direction, and then divided by the dimension of a size of the block. No, sorry, I made it the other way around. So dxij is the displacement of the jth corner in the ith direction. All right. I think that this will be enough for today. So see you tomorrow, and thank you for your attention.
You said it's the size of the cube. Do you mean the surface area of the cube?
No, size, dimension.